Once we are done with the study selection, data extraction, and assessment of risk of bias, the next step is to look at how we combine results across studies. This is where meta-analysis comes in. Now let's start by clarifying what a meta-analysis is. The overall aim of a systematic review is to summarize all the available evidence in a clear, unbiased, and structured way. We want a synoptic view of what the research tells us. A meta-analysis is the statistical part of that process. It is a technique that allows us to combine results across multiple studies and calculate a single summary estimate of the effect. So instead of just describing what each study found, a meta-analysis gives us a quantitative answer to our research question. It helps us increase precision, reduce random error, and better estimate the true effect of an intervention. However, not every systematic review includes a meta-analysis. Historically, one major criticism of meta-analysis was that it might involve mixing apples with oranges. In other words, people worried that we were combining studies that were too different to be meaningfully pulled together. But the key question is, what are we actually interested in? If we are interested in the overall effect of fruits, then combining apples and oranges may make sense. However, if different fruits have different effects on outcomes, for example, on nutritional benefit or taste satisfaction, then pulling them without checking similarities could be misleading. The same logic applies to healthcare research. Before pulling studies, we need to ask, are the populations similar? Are the interventions comparable? Are the outcomes measured in a similar ways? And meta-analysis is not about blindly combining everything. It's about combining studies thoughtfully and appropriately. Now let's look at some important principles of meta-analysis. First, meta-analysis moves us from the study level to the outcome level. We don't just summarize studies, we analyze specific outcomes across studies. Second, meta-analysis is a statistical technique, not a synonym for a systematic review. A systematic review can exist without a meta-analysis, but a meta-analysis should always be part of a systematic review. Third, not all data can be included in a meta-analysis. Some outcomes may be reported differently or lack the necessary numerical information. In those cases, the results should be synthesized narratively instead. And finally, we usually start by pulling studies widely and then check whether the effects are similar across the PICO components. If effects differ across these components, we may need subgroup analysis or separate meta-analysis. This slide shows a pairwise meta-analysis and the forest plot. In this plot, each horizontal line represents a study. The square shows the study's effect estimate, and the line shows its confidence interval. The size of the square reflects the weight of the study. Larger studies usually contribute more to the pooled result. And at the bottom, the diamond represents the summary or pooled estimates. This combines the result of all included studies into one overall effect. And the vertical line represents no effect line. If the diamond is clearly on one side of that line, it suggests a benefit or harm. So, a pairwise meta-analysis allows us to visually compare study results, allows us to assess consistency, and effect estimate an overall effect. This makes the evidence easier to interpret for researchers, clinicians, and policymakers. And one final important point to remember here is that a meta-analysis is essentially a weighted average. Each study does not contribute equally to the final pooled estimate. Instead, studies are given different weights as shown in the square, based on the factors like variability. So a key question in meta-analysis is how should we assign weight to each study? The way we assign these weights depends on the model we choose. fixed effect or random effect model. These are the two main statistical models used to combine results across studies. The key difference between them is the assumptions they make about heterogeneity or variability, or in other words, how much the true effects are allowed to vary across the studies. Another important point is that the choice of model should be pre-specified in your protocol, not decided after seeing the results. So before you run a meta-analysis, you should already have a plan for which model you will be using and why. To better understand fixed and random effects models, we need to think about two types of variability. The first type is within study variability, also called variance. This reflects random error within each study and is shown by the width of the 95% confidence interval. It mainly depends on sample size. Large studies usually have narrower confidence intervals. And the second type is between study variability, also known as heterogeneity. This reflects real difference between studies, such as differences in populations, interventions, or methods. Fixed and random effects models treat this between study variability differently, and that's what leads to different pooled estimates and different study weights. The fixed effects model assumes that there is one true effect that is the same in all studies. In this model, any differences we see between study results are assumed to be due to random sampling error only. In other words, between study variability is assumed to be zero. Because of this assumption, the fixed effect model gives more weight to larger studies, since they are considered more precise. And this model works best when studies are very similar. Heterogeneity is low, and we believe the true effect is essentially the same across studies. The random effect model takes a different approach. Instead of assuming one true effect, it assumes that each study estimates a different but related true effect. These effects follow a distribution, and the meta-analysis estimates the mean of that distribution. So here, between study variability is not zero and must be considered. Because of this, the random effects model gives more weight to smaller studies compared to the fixed effect model. And this model is more appropriate when there is substantial heterogeneity. Studies differ in populations, interventions, or settings, and when we expect true effects to vary across studies. However, compared with fixed effects model, random effects model also lead to wider confidence intervals, reflecting greater uncertainty. Before we jump into the details of meta-analysis, let's talk about effect measures. Effect measures describe how we quantify the difference between groups in a study or in a meta-analysis. The type of effect measure we use depends on the type of outcome. For dichotomous outcomes, the outcomes with two possible states, such as yes or no event or no event, we can have relative or absolute measures. For relative measures, we have risk ratio or odds ratio. And for absolute measures, we have risk difference, which tells us the actual difference in event rates between groups. And for continuous outcomes, outcomes that are measured on a numerical scale, such as blood pressure or quality of life scores, we have mean difference when all studies use the same scale, or the standardized mean difference when studies use different scales. And we put the results on a common scale so they can be compared and pooled across the studies. Some outcomes don't fit neatly into simple dichotomous or continuous categories. For example, for ordinal outcomes, such as severity levels or rating scales, we have two main options. We can dichotomize the outcome and use standard dichotomous effect measures, or we can use a proportional odds model, which keeps the ordered structure of the data. For counts and rates, such as the number of hospital admissions, we usually use a rate ratio or a rate difference. For time to event outcomes, such as time until relapse or death, the most common effect measure is the hazard ratio. So again, The choice of effect measure depends on the type of outcome. As we have introduced previously, a meta-analysis is a weighted average. Instead of simply averaging the results of different studies, we multiply each study's estimate by a weight, add them together, and then divide by the total of the weights. So the pooled estimate is the sum of estimate times weight divided by the sum of the weights. This means that some studies contribute more to the final results than the others. Again, the key question becomes, how do we decide the weight for each study? We talked about this earlier in this video, that we assign weights depends on the meta-analysis model. In a fixed effects model, the weight is based only on the study's variance. So the weight is 1 divided by the variance. This means more precise results, usually from larger studies, get more weight. In a random effects model, the weight includes both the within-study variance and the between-study variability or heterogeneity. So the denominator becomes variance plus heterogeneity. This reduces the dominance of large studies and gives relatively more weight to smaller studies. This slide shows the weighting methods for dichotomous outcomes. So there are several common weighting methods such as inverse variance and Mantel-Haenszel methods. Both could be used for either fixed or random effects models. And there are methods that could be only used for one model approach. For continuous outcomes such as blood pressure or quality of life scores, the main weighting approach is inverse variance. This applies to both fixed and random effects models. Now let's briefly distinguish between subgroup analysis and sensitivity analysis, which serve different purposes in a meta-analysis. First, subgroup analysis. It divides studies into groups based on certain characteristics, for example, treatment duration, age group, or study quality, and then tests whether the effect differs between these groups. The goal of subgroup analysis is to explore effect modification. Are the results different in one subgroup compared to another? However, subgroup analysis should be pre-specified and interpreted cautiously because multiple comparisons can increase the risk of false positive findings. Next is sensitivity analysis. Sensitivity analysis does not focus on differences between groups. Instead, it tests how robust the main results are. We repeat the meta-analysis while changing certain decisions, such as which studies are included, the method of analysis, or how missing data are handled. Then we check whether the overall conclusions change. If the results remain similar, we can be more confident in our findings. If they change a lot, it suggests the results are sensitive to methodological choices. So in summary, subgroup analysis asks, do effects differ across groups? Sensitivity analysis asks, are the results stable under different assumptions? Now let's see a real-life example of meta-analysis and how to interpret it. This forest plot compares extended duration treatment with standard duration treatment for smoking cessation. On the left, you could see the individual studies, along with the number of events, the total number of participants, and the weight each study contributes to the meta-analysis. Each study is shown as a square, and the horizontal line represents its 95% confidence interval. Large squares mean the study has more weight, and the vertical line at 1 represents no difference between the two treatments. And because the outcome is a dichotomous outcome, so we use the risk ratio as the effect measure. And that also means when the risk ratio is 1, it means no effect. Here, the studies are divided into two subgroups, extended treatment shorter than 12 months and extended treatment of 12 months or more. At the bottom of each subgroup, you can see a diamond. For the shorter than 12-month group, the pooled risk ratio is 1.12. which slightly favors extended treatment. For the 12-month and over group, the pooled risk ratio is 1.54, suggesting a stronger benefit of extended treatment. And at the very bottom, we see the overall pooled estimates across all studies and the two subgroups, a risk ratio of 1.18 with a 95% confidence interval from 1.05 to 1.33. Because this confidence interval does not cross 1, the result is statistically significant and favors extended duration treatment. This plot also reports heterogeneity shown by I-squared value and the statistical test here. This tells us how much of the variance between studies is due to the real differences rather than chance, and this is an indicator to help us decide whether we should use fixed effects model or random effects model. So, this case example shows how meta-analysis combines results from multiple studies, weights them appropriately, and provides a single interpretable summary of the evidence. To summarize this video, when conducting a meta-analysis, systematic reviewers need to make several key methodological decisions. First, they must choose the statistical framework, how the data will be analyzed, whether it is a pairwise meta-analysis or network meta-analysis. They also need to select the model, such as a fixed effects or a random effects model, which reflects the assumptions about variability between studies. And they also need to decide the effect measure, such as risk ratio for dichotomous outcomes or mean differences for continuous outcomes. They also need to choose the method for weighting studies, which determines how much influence each study has on the pooled result. And importantly, all these decisions should be made a priori and clearly specified in the systematic review protocol. This helps prevent selective analysis or choosing methods based on the results that look most favorable. By pre-specifying methods in advance, we improve the transparency, credibility, and scientific integrity of the meta-analysis.